which is kind of a review chapter, and then it's also going to set the stage for what we're going to do for the next, probably 6 to 5 chapters after this, okay? So the majority of the course, at least up until spring break in theory, is going to deal with this idea behind synthesis, right? And so all we're going to be leading up to is the ability to make whatever compound we want given really basic starting materials. And to do that, we have to have all of these various reactions, okay? And so we're going to start that with chapter 7, chapter 8-ish, but we're also going to start to redefine some things in chapter 6 just to refresh your memory about a couple of specifics with respect to reaction mechanisms, etc. Okay? All right, so this chapter is going to be broken down into a couple different sections. The first thing we're going to do is we're going to refresh on the topic of thermodynamics. Then we're going to talk about kinetics. And then we're going to go back to this idea behind arrow pushing and using arrows to track our various mechanistic steps. Okay, so when we start with thermodynamics, we're going to start with this concept of enthalpy. So does anyone remember what enthalpy is? Enthalpy. Heat, right? So delta H, right? Enthalpy was a thermodynamic function. We gave it the nice little letter H, right? And we defined it as the heat of a reaction. Okay, so when we're talking about anything in thermodynamics, we're always talking with respect to the system as well as the surroundings, right? So whatever happens to the system is the reverse of what happens to the surroundings. In chemistry, who do we define as the system? What are we really interested in knowing stuff about? What are we always making things occur? What do we do in the lab? We do bonds. Reactions, right? So the system we tend to get rid of really early, and we just define this in terms of our actual reactions, okay? Just as a reminder, I use RXN as an abbreviation for reaction. Okay, so a couple of things to note. If we go back to this idea behind bond formation, and I may have to take this off. It's moving. What? It's not my heat. It's moving my thing. Okay, so we go back to this idea behind bond formation, right? We go back to the idea behind molecular orbital diagrams. Let's say that we have something like hydrogen, so H bound to H. We have our little atomic orbitals for hydrogen. How many electrons does hydrogen have in its 1s orbital? 1 electron for both guys, right? And a bond forms, a nice bonding molecular orbital, when the potential energy of those 2 electrons and those 2 atomic orbitals is lower, right? When they constructively combine, we get our nice little bonding MO, okay? So again, bonds form when the combination of those 2 orbitals lowers the potential energy comparatively to them just being by themselves out in space, okay? So if we have lowered potential energy in forming a bond, if we want to break a bond and we want to take those guys apart, what are we going to have to do? Add energy. We're going to have to add energy, right? So as a note, bond breaking always requires energy. Always have to have an input of energy to break a bond, okay? Where does that energy come from? Heat, right? So the heat of the surroundings, the heat of the molecules in the surroundings, where our molecules, our reactants are actually getting this energy to break various bonds, okay? And so that's what enthalpy is in terms of our chemical reactions. It's the actual heat or the energy that's being supplied to break a bond, okay? Okay, so just as a note, there are 2 different ways that we can break bonds in our little organic reactions, okay? The first one we've kind of dealt with already because we've gone through general chemistry, etc. That is called heterolytic bond cleavage, okay? And so hetero, what does that mean?
Same,
different. So hetero means different, and in a heterolytic bond cleavage reaction, the 2 different atoms that are part of that bond are going to end up with different electrons afterwards, okay? And so when we talk about this, we're always going to use our arrow, right? So a nice little 2-headed arrow. What does the tail represent in our little arrows?
The beginning.
Where tail represents where they're starting from, right? So the tail of our arrows is always where the electrons start. So electrons start. And then the head is what? The head is where they're going to, right? So we've got our head, this is where they go to, and we've got our tails where they start from, okay? So in a heterolytic bond cleavage reaction, the electrons that are in the bonds between our two atoms are going to go specifically together to one of the atoms, okay? And we're going to use, again, our nice two-headed arrow for that type of reaction. The result of that, we're going to end up with a pair of electrons on one atom and a deficiency of electrons on the other, and it's going to produce a negative charge as a formal on one and a positive formal charge on the other, right? So a positive formal charge is called a cation, a negative formal charge is called an anion. In the production of these heterolytic bond cleavage reactions, what do we produce at the end? We produce cations, we produce anions, but overall, what do we call these charged molecules? Together they're neutral, but this is an ion, right? So heterolytic bond cleavage reactions produce ions. These are what we call ionic reactions or polar reactions, because the result of them always leads to the production of ions, or at least semi-production of ions. Okay, so those are heterolytic bond cleavage reactions. There is another way to break a bond, though, and that is what we call homolytic bond cleavage, okay? So homo means same, and in a homolytic bond cleavage reaction, what's going to happen is the two atoms that are forming that bond are going to end up with the same number of electrons. Or that bond, which has two electrons in it, is going to be split evenly between atom X and atom Y, okay? When we do our little arrow pushing for this, we're not going to use our two-headed arrow. We're actually instead going to use what's called a single-headed arrow. This is also termed a fishhook arrow. Fish hook, it would have two H's, okay. Fish hook arrow. And again, why do we call it a fish hook? Looks like a lure, right? Is that what this is? A lure?
Yeah.
If you go fishing, the hook? Okay, yeah, okay. It looks like a lure, right? So again, this guy's supposed to be representing the movement of one electron from this bond to one guy, the movement of one electron to the other guy. So instead of producing ions, what we end up with here is unpaired electrons on both of the atoms. If you have a species with an unpaired electron, what is that called? Radicals, right? So heterolytic bond cleavage reactions always end up in the production of radicals. We will touch on this again because we have to go over radical reactions, but for the most part, heterolytic bond cleavage is what we do, and these are going to be the majority of the reactions that we actually talk about.
Why come this one doesn't have radicals don't have the plus or minus thing?
Because if you actually look up the formal charge, it's zero. They're neutral. Radicals don't have formal charge, again, because the formal charge is zero if you actually calculate it. Okay. All right, so now that's just a little brief basics on what enthalpy is and how we actually go about breaking bonds. So then number two, how did we determine the enthalpy of a reaction? In theory and general chemistry, and it was many, many eons ago, we taught you a couple different ways, right? But at the end of the day, and I said, hey, here's a reaction. I want to know what the delta H is for this. Without having to do any experimental stuff, what would you do?
Add up all the delta H's?
Something about that, right?
Final minus.
Something final minus initial. There were values, right? You'd look them up in the back of the book. You would calculate it. Right, so there were always data, right? You could always use various enthalpies of formations or various other enthalpies to calculate the enthalpy for a reaction. One way that we taught you was using what are called bond energies, okay? Now, in this book, we call them something a little bit different. These are called bond dissociation energies, or BDEs. They're equivalent to bond energies in general chemistry, okay? Now, a thing to note about this, these are calculated values, right? They're standard state calculated values. They are calculated for homolytic bond cleavage, not heterolytic bond cleavage. The majority of the reactions, again, that we will do is heterolytic. So these are going to be just estimated values, but they do give you a general idea of what the delta H is for an overall reaction, okay?
This one is only for homo.
Homolytic, but we're going to use it kind of interchangeably, okay? Okay, so now these will allow us to calculate, or at least estimate, the enthalpy for a reaction, that's not my highlighter, at standard state as a note. So this guy up here, this little zero, this little knot, what does that refer to? Standard state, what does standard state? Standard temperature pressure, it mainly has to do with concentrations or partial pressures of reactants and products, right? So if we're at standard state, we're dealing with gases. The partial pressure of our reactants and products is 1 atm. If it's concentrations, it's 1 molarity, okay? So just as a reminder, these are very specific conditions. But again, we can utilize it to kind of estimate various things. Now, how are we going to do that? We're going to sum all of the bonds that are broken in a chemical reaction. So we have the sum of the bonds broken, and we're going to subtract from that the sum of the bonds formed, because again, it requires energy to break bonds. We're going to see a release of energy when bonds actually form. And so that's why we have a positive for bonds broken, and we're going to get a negative overall for bonds formed. Now, depending on the reaction, it's going to depend on whether or not the overall value of delta H is negative or positive, okay? Okay, so let's keep that in mind. Now, there are two possibilities for delta H, right? Delta H can be negative or delta H can be positive. If delta H is negative, what does that mean? What do we call that type of reaction? Not delta H, but we'll get to spontaneity in a second. So delta H of negative, what do we call that? Exothermic reaction. What was the big caveat behind this, right? Right, so energy is released. And where is that energy coming from? We have our reactants, right? Let me get back to black here. Our reactants are at a higher enthalpy or a higher energy state than our products. So in the overall course of the reaction, in going from here to here, this change in energy is going to be released to the surroundings. How does that manifest in the surroundings? What happens, right? It gets hot in the surroundings, okay? All right, so again, we've got our delta H here. This is negative. These are our exothermic reactions. What about if delta H is positive? Delta H being positive, what do we call that? Endothermic. And in terms of our little energy diagrams, what that means is that our reactants are at a lower enthalpy state than our products. So to get them up here, we need to supply energy, we need to supply heat. How does that manifest in the surroundings? Temperature gets what? Colder, right? Because again, our reaction is taking in that energy to get these guys up to this point and have the reaction actually go, okay? Okay, so endothermic, exothermic. A couple other things to note. We're going to continue to utilize these reaction coordinate diagrams. So have you seen these before? We've looked at these before-ish, right? So for this guy, we've got enthalpy on the y-axis, but what is on the x-axis? What does that mean, reaction coordinate? So just overall, I know these are a little bit weird. It's more of like a model for us to understand various things. But what we're looking at here is like reaction progress, right? We start here as a reactant. As the reaction progresses, we move to the products, okay? And we're going to talk about various other little points in there in one little second. Okay, all right, so enthalpy, heat, great, good. Now, going back to those bond dissociation energies, one thing I could have you do is calculate the change in enthalpy for a reaction, right? So for example, let's say I've got this guy. What is this called? What is this 1, 2, 3? What is the name of this molecule right here? So remember, all the zigs and zags are carbons. No. What's the parent chain?
3, so
3. Where is the constituent coming off of? 2. What is it?
2-methyl isopropyl.
Where is the iso coming from?
Sorry.
2-methylpropane. Good. Okay. All right. So we can say that 2-methylpropane. I'd hope that it'd be really easy to see, but it's cool. Okay, so we have our 2-methylpropane. It's reacting with chlorine, right? Forming a 2-chloro-2-methylpropane and then HCl. Okay. So now I would suggest that you guys look into the book to actually get those bond dissociation energies, because in my slide I don't have all of them that you actually need to calculate this. But just as a note, you should consult the book, okay? All right, so if we're going to want to use our bond dissociation energies to estimate delta H for this, what do I need to know? I've got delta H is equal to the sum, as a note, Greek sigma, the sum of who? Who comes first?
Bonds broken.
Bonds broken, right? Because we always have to supply energy to break bonds. So this is bonds broken. And then who am I subtracting from that? Bonds formed. Okay, so now, who's been broken? What bonds did we break? Which side should I look at to figure out which bonds have been broken?
HC, well, the products, what's
So where are we going to break bonds at? Over here or over here?
over there?
Over here, reactants, right? So we look at this. There's an easy one of a bond that we break, right? The Cl2. So one bond that we break is this guy, and I'll go to red for this, broken. What's another one that we break, though?
The C and the H.
All right, so if we look at the products, we have a chlorine attached to that 2 position. Over here, what's at that 2 position instead that's implied, that's never written? H, right? So we have a nice H here that also gets broken, okay? So those are the 2 bonds that are breaking. What bonds are forming? All right, so we have an H and a Cl. That bond is forming. What else?
CCl.
The carbon and the Cl. This bond is also forming, okay? So now, what do?
You go to your little
Look up those values, right? And so this is the kind of the thing to note, that this guy, this bond here, is very specific. It has 3 methyl groups to a carbon that's to a hydrogen, okay? So when I look up this guy, I find that the bond association energy for it is 381. I look up the chlorine, I find that the bond association energy for it is 243. And then when I look up these 2, I get where did I go? 331, and then HCl I get a 431, okay?
Don't that have to be negative?
Well, hold on. So
Okay.
I'm just looking them up so that I can write them down, yes.
Where did you get your 381?
381, if we look in the chapter. I know it's not on the slideshow, that's what I was
okay.
saying, yeah.
Sorry.
So what I'm looking up here, just as a note,
So just
is CH3, 3C, and then H. This guy in the book is 381.
gotcha. Sorry.
It's really ugly. Okay, so with that, we've got bonds broken. So it's my 2 reactants here. I've got 381 plus 243. Minus bonds formed, which are my products, 331 plus 431. So when I add the 2 together and then subtract the 2, I end up with a minus 138. And then I've been really negligent with units. The units here that I'm using are kilojoules per mole. You also have the option of kilocalories, but I don't get that. I don't know why. It's a biological thing, using calories as opposed to kilojoules.
We don't have to go into this class.
No, I don't use calories. Who wants to know that, really? Okay, so is this reaction endothermic or exothermic? Exo, good. Okay. Something gets through from general chemistry. Okay, so now with that's the example. I have 2 problems that I want you guys to do on your own, but I would divide them up.
How do we do with the values?
You don't have to look up the values. Don't you have access to the book?
Yeah, I do. I can give the values.
Okay, so we had done these problems in class. I'm going to quickly go through and use those bond association energies to estimate the change in enthalpy for the following 2 reactions, right? So to do this, what we're looking at is the, let's see, if we're looking at delta H, we're using these bond association energies, and what we're going to do is we're going to sum all of the bonds that we break. So sum of the bonds broken, or bonds break, I guess. I'm going to subtract from that the sum of the bonds formed. Right, so we have to go in and we have to look at these and figure out what bonds we broken and then what bonds we form. We look up the values, we sum them, and then we subtract the 2, okay? So for A, what we're looking at here is we're taking this molecule and we're turning it into this molecule. So again, I have to recognize what's actually happened, right? We had a carbon iodine bond here that in our product is no longer there. Now it's been replaced by a carbon alcohol bond or carbon oxygen bond, right? So first off, we have broken this bond, okay? And so we're going to find the bond dissociation energy for that. Second, if we look at our water molecule here, the other bond that we have broken is an OH bond, right? Because again, this oxygen essentially becomes the new bond to carbon. So to do that, we have to break this hydrogen-oxygen bond so that can occur, okay? So we have two bonds that are broken. The bonds that we form are over on our product side. So we have now a carbon-oxygen bond. And then we also have a new hydrogen-iodine bond as our product as well, okay? Okay, so I go in and I look up these bond association energies. I'm going to start with our reactants, the bonds that we break. So this guy, what I'm looking for is a carbon that is bound to an iodine that is then on the other side, essentially surrounded by three different CH3 groups, right? So this is going to be carbon iodine with 3 CH3 around it, right? And so when I look this up, I get a bond association energy here of that's how I messed that up. So we get a bond association energy of a 209. And again, the units here are kilojoules per mole. And then the other bond that we're breaking is this HOH bond, right? This bond. And when we look that up, we end up with a 598 kilojoules per mole. So these are the bonds that we break. If we go over here and do the same thing for the bonds that we form, we're looking for a carbon that is attached to an alcohol or a hydroxide that on the left is essentially attached to 3 different methyl groups, right? So this bond, when we look it up in our table, ends up being a 381 kilojoules per mole. And then this H to I, this bond specifically, when we look up in our table, ends up being a HI is a 297. Right, so now we're going to take the sum of the bonds that we break, right? So that's going to go first. Bonds broken are our 209 plus our 498. And we're going to subtract from that the sum of the bonds formed, which are these guys, right? So this is 381 plus 297. We add everything together, and then we subtract. We're going to end up with a positive 29. And again, the units here were kilojoules per mole. And that is our delta H for reaction A. Okay, so same thing for reaction B. So this guy is A. Going to go down here for B. We'll notice again what's changing between our reactants and our products to actually determine who's being broken and who's being formed. So in our reactants, we've got a carbon attached to 2 hydrogens that is essentially replacing, or one of those hydrogen carbon bonds is being replaced in the product. So we still have one of those hydrogens, but the other one has been replaced with a bromine. The bromine is coming from the dibromide in the reactants, and it's being replaced with an HBr in the products, okay? So the bonds that we're breaking here are 1 and 2, right? Whereas the bonds that we're forming are, we've got 1 is bromine carbon, and then 2, an HBr, okay? Okay, so same thing. We'll go and look these guys up. For the first one, that carbon-hydrogen bond, we've got a carbon that's attached to a hydrogen, but now the other stuff that it's attached to is a little bit different, right? The first one had 3 different methyl groups around it. This has a hydrogen, and then it has 2 methyl groups around it, right? So this is this CH32HCH. When we look this up in the table, we find a bond dissociation energy of 397. And then we're looking at BR. That has a bond association energy of 193. And again, these are all in kilojoules per mole, right? So this is the guy that we're breaking. And then over here for forming, we're looking at a carbon to bromine that's got a hydrogen and then 2 methyl groups to the left, all right? When we look this guy up, it's got a bond association energy of 285. And then finally, we get an H and a BR. And this guy has a bond association energy of 368. Okay, so then we utilize these guys. We've got delta H is equal to the sum of the bonds broken. So this is our 397 plus our 193 minus the sum of the bonds formed. So this is our 285 plus our 368. When we add these guys together, it looks like we get a minus 63 kilojoules per mole as the delta H here. So we can go ahead and highlight, so answer to B and then answer to A. Again, these values that we've used in here will have to be given to you, right? You can't just like make this stuff up, but you do have to know exactly what types of bonds are being broken and be able to identify that in the table, right? Same thing with the bonds being formed. Okay, all right, so.
Start over.
Pardon me. No, I can't do it.
Did you record it?
No, I didn't record it. That's what, okay. So anyway, okay, entropy of the universe must increase. In these situations, we're seeing an increase in entropy, right? But is this the universe's entropy that we're looking at here?
That's the system.
That's the system, right? This is our reaction. What else is the system? What else does the universe encompass? It's not just the system, it's also
It's
the
our surroundings.
surroundings, okay? So here, we always saw these increases in entropy for our reaction or our system, but we also always have to take into account the surroundings in determining whether or not this is positive, whether or not we have a spontaneous reaction, okay? What happened to this equation? Do we ever deal with this again in 152? So we think in terms of the surroundings, right? Because that's going to affect things. The surroundings gets replaced by something because the surroundings, the entropy of the surroundings, is going to be influenced by the enthalpy of the reaction, right? If a reaction was exothermic, if it was endothermic, what's happening to the temperature of the surroundings? Increasing or decreasing, okay? So in reality, or what we do overall in chemistry, we get rid of this reaction or get rid of this equation and replace it with Gibbs Free Energy, right? Gibbs Free Energy was our chemical potential energy, right? It was essentially that second law of thermodynamics just rearranged, okay? Now, for Gibbs Free Energy, if we want something to be spontaneous, what is the sign of delta G? Negative, right? So negative values of delta G led to overall spontaneous reactions, right? So again, spontaneous being it will happen without any outside intervention, okay? What about delta G's that were positive? Delta G's that are positive, these guys are going to be non-spontaneous reactions. If a reaction is non-spontaneous, does that mean it will never occur? No. What has to happen, though, for it to occur?
They just need to make it the right,
You have to add
setting, environment.
We have to add energy, right? It's not going to do it on its own. You have to add energy from somewhere else, okay? Okay, so in terms of words, we didn't really introduce delta G being negative, delta G being positive, but these guys actually have specific definitions. They have their own name as well. So delta H for negatives was exothermic. For delta G's that are negative, these are called exergonic reactions, okay? So spontaneous delta G of negative, it's called an exergonic reaction, whereas non-spontaneous reactions, delta G of a positive value, these are called endergonic. So they have their own little special name. Endergonic, exergonic, it's very, but we don't use them that much.
Oh, then I forget.
I mean, you do, but it's like, why don't they introduce that in general chemistry? I don't know why they wouldn't do that, but they don't. So, yeah.
What is that? What letter is that?
Which one?
The bottom one, spontaneous reactions? No?
Delta G. Those are my capital, those are my cursive G's.
Oh,
So this can get confusing. You can have an intergonic, exothermic, and
Yes.
But it's still the same thing as like.
exergonic, exothermic?
Yeah, so X goes with the negatives, N goes with the positives. Okay, so with that, okay, delta G has now been essentially replaced with an enthalpic term. So delta G depends on the enthalpy of the reaction, and we call this an enthalpic term, as well as the entropy of the reaction, our delta S. So this is what we call the entropic term for delta G. So both the enthalpy and the entropy go into affecting whether or not delta G is positive or negative, okay? So if we look at a reaction like this, right, where we have whatever this is, okay, this is actually a reaction that we'll look at as a paracyclic reaction. This is called the diene, and this is called the dienophile. When we take that and we combine them and we cyclize that and we end up with a cyclic ring here, what happens to delta S for this reaction?
So
It's-
should have one, so delta S is, okay.
So we take two things and we make one, right? So we're decreasing the freedom of motion of those reactants, right? So we're decreasing the entropy. So for this reaction, we could say, just by looking at it, that delta S would be negative, right? We're decreasing entropy. If I tell you that this reaction is spontaneous, though, so I tell you that delta G is also negative, and again, that's a delta G, my apologies. What could you tell me about the enthalpy of this reaction?
The heat was
So again, if we go back to our entropic term, if we're decreasing our entropy, we have a negative T times a negative overall that makes us a positive value, right, for our entropic term. If this is positive, but we know overall that this is negative, what has to be the value, or what has to be the sign of the enthalpy?
That has to be negative.
It has to be negative, and most importantly, it also has to be larger than whatever this ends up being, okay? So that can tell you right off the bat that this is an exothermic reaction because, again, delta G's got to be negative overall, okay? Okay, so now it's not just entropy that's determining whether or not something is spontaneous, it's also taking into account the enthalpy of the reaction. Let me make sure I get everything here. Spontaneous, non-spontaneous, okay, cool.
You've actually recorded this. Right?
Yeah.
Yeah, I'm gonna have to go back to this.
So, yeah, so formulating.
Okay.
I'm sorry.
Yeah.
Okay. Can you say that again really quick in like a minute?
Yes.
Like 30 seconds, and explain it to me like I'm 5.
I can't. It's
Like I'm
organic
10.
chemistry. Okay, explain to you like you're 19, which
Okay,
I think
yeah,
Eric
yes,
is.
please
So,
do
so
Okay.
again, we can estimate or just determine the sign of delta S by looking at the fact that we have two things and we're making one.
Okay.
Right. So we know, okay, we're decreasing randomness, we're negative for delta S. Okay. If delta S is negative and we plug it into our little equation, there's always a negative in front. It's delta H minus T delta S. Right. So because of that, if this is negative, this times this makes this overall a positive term, right? The entropic term is positive, which is bad. It's unfavorable for spontaneity. If this reaction, and I'm telling you this, is spontaneous, delta G is negative, then enthalpy has to be negative and it has to be larger than whatever this entropy term is. If it's not, then the overall sum would be positive and it'd be non-spontaneous. So again, I'm telling you this, you're estimating this, you're making a conclusion about this. Now, it could be something different, right? I could give you this, you could make some sort of broad assumption about this. Could you also now calculate this,
No.
As a value?
delta H?
If you have that
Is my delta G still
bond
negative?
dissociation energy.
If you have the BDEs, or you have the bond association energies, could you calculate delta H
Yeah.
for this reaction?
Yes.
Yes. Okay. So that's kind of the little differences or the little tweaks. You can calculate this now as long as I give you the bond association energies. You can also estimate the sign of that, and you can tell me something about delta G
What is
correspondingly.
T in kelvins or what is
T is in kelvins, yeah. Yes.
How would you know, like, would delta S most likely be given to us then?
No, again, we're getting the delta S from the fact that we're taking two things and we're making one, or we're cyclizing them.
Okay.
We're taking away our reactants' freedom of motion by putting them in the cyclic ring structure, so we're decreasing that freedom of motion overall. So we can assume that delta S is negative for that,
Okay.
because we're decreasing. These guys products have less freedom of motion than reactants. If it was the reverse, it would be positive, and we
We're
can say that.
going from a ring
To free, yeah. Okay, all right, so delta G, right? It tells us whether or not a reaction will occur, okay? Now, let's imagine that we have some sort of just random reaction go to something like this. A combining with B going to make C and D, okay? And let's say that I tell you, okay, well, we calculated delta G. We calculated delta G for this reaction, and it's like 100 kilojoules, minus 100. That's the big thing, okay? Okay, so what do you know about this reaction? Let's say that we only have reactants initially. Let's say that's at standard state. So this is, let's say, 1 ATM and 1 ATM. What do you know is going to happen?
As soon as you see negative 8 100, you know that it's spontaneous off the bat.
Spontaneous, right? It's spontaneous in which direction? Because it's forward. It's always forward. The way we're always writing it, it's always spontaneous in the forward direction.
Oh.
Right? So we know that A and B are going to go, they're going to make C and D, right? When is it going to stop? Does all of A and B go to C and D?
When A or B went down.
To equilibrium, right? Is that why the 2 arrows are there?
So that's the big thing, right? So Gibbs Free Energy tells you the amount of work that can be done, or the free energy that can be derived from a reaction at standard state conditions. The minute we let this reaction start, right, what's going to happen to the concentrations of A and B? They're going to decrease, right? And there's a relationship between Gibbs Free Energy and the concentration of reactants and products, right? So as these guys start to decrease, we're going to see a decrease in free energy, until what point? Until we reach delta G equal to 0, until we reach equilibrium, okay? So now, at equilibrium, do we have all C and D and no A and B? No, but what will we have? How do we define how much product versus reactants we have at equilibrium?
Equal amounts.
Is it equal amounts? It's equal rates at equilibrium.
Oh, equal rates. Oh.
There's a ratio. How do we define that ratio?
C divided by A.
Right, so our equilibrium constant, right? And this was overall, just in a really brief summary, the concentration of products over reactants. And again, the rates of their stoichiometric coefficients, but that doesn't matter, right? That's all we really care about is products over reactants. Okay, so this reaction will continue to go until it reaches equilibrium. At equilibrium, we can harvest no more energy, delta G is 0, and that's where everything is always going to begin with, okay? So there is a relationship between Gibbs Free Energy and the equilibrium constant. Again, KEQ is the equilibrium constant, and it is given here. You don't need to know it, but all I want to make note of is kind of some relative amounts of delta G and kind of that ratio of products to reactants at equilibrium, okay? So let's say we had a Gibbs Free Energy of minus 17, which is not very much in terms of kilojoules per mole. At equilibrium, 99.9% of the reactants have turned to products, right? Is there still some product, or is there still some reactant left?
A little bit.
Yes, right? On the other side, let's say positive 17, at equilibrium, the product to reaction ratio is 0.1, right? So if there's lots of reactants, there's not a lot of products. Is there still a product?
Yes.
Yes, right? When would this be 100?
Never in life.
What would it be the mathematical necessity for this to be 100? So if delta G was infinite, then KEQ would be 100, right? Or minus infinite, or whatever you want to look at like that. So I guess what I'm trying to say, what I'm trying to make note of here, is regardless of the reaction, there will either always be some reactant or there will always be some product at equilibrium. Okay? It may be one molecule to a billion, but there will still be one molecule. Okay?
So the only time it would ever be 100% is if you entirely took it out, but you couldn't do that as well.
Yeah.
So even the best, most efficient reactions, you're never going to have everything turn in product.
You can manipulate things using the Shot-Ayres principle, trying to pull away products, but yes, the whole grand scheme of things, reactions are always going to have, especially in terms of, I'm doing this more in terms of biology and biochemistry, there's always going to be a product, there's always going to be a reactant left. It's always going to be there. No matter if this is positive or this is negative, there's always going to be a distribution of both. Okay, all right, so That's
Wait,
what
about the
Yes.
RT, ln, natural log?
natural log of KQ. This is just, oh darn it. I don't like, yeah, it's okay.
We don't have to know.
You don't have to know that,
Okay.
no. All I'm trying to do is say, hey, there's a relationship between delta G and K. K is the equilibrium constant. Reactions are starting, and they're always getting to equilibrium. And delta G is the energy or the work that we can do in letting them get there. Okay? Okay, so that is thermodynamics. That was a brief review of thermodynamics. Now, as a note, what does thermodynamics tell us? Long-term energy, stuff like that, but mainly whether or not a reaction is what? Spontaneous, whether or not it will happen, right, without any outside intervention. Now, a good example of a spontaneous reaction that still doesn't ever really happen is diamond turning to graphite, right? Diamond is an allotrope of carbon, it's solid carbon. Graphite is solid carbon. That is a spontaneous reaction. Diamond should spontaneously turn to graphite. Why doesn't it? Because you don't, does anyone have a diamond ring?
No,
Or
we're
diamond
bored.
earrings? I don't know, diamond
We're
something?
bored.
Nothing?
Yeah, we're bored.
You can use
Is it turning to graphite?
Slowly, like super slowly. Doesn't it eventually do it after, like, maybe a million years?
Million years, but why? It's spontaneous. What else are we working on? What else are we looking at here if a reaction is spontaneous but it doesn't actually occur?
Surrounding? Everything around it?
Entropy.
Not entropy, so we're done with thermodynamics. That's what
Oh.
thermodynamics tells us. Entropy, enthalpy, it all is about will a reaction occur? What else are we missing if it doesn't occur even though it's spontaneous?
Rate.
Great, right, kinetics. So,
Also how fast, because the time.
right. So there are two things that affect our reactions. Thermodynamics, whether or not something will occur, as well as kinetics, right? So we do have to review very briefly some concepts learned about the kinetics of reactions. Okay, so what does kinetics deal with? We just mentioned it.
Rates.
Rates or speeds of chemical reactions. What were some of the various factors that affected how fast a reaction would occur?
How much product? Concentration, I think.
Okay, so we're going to start with that one because there's other things, and I don't want to get off topic. First thing that affects the overall rate of a reaction is concentration of reactants, right? So let's imagine that we had some sort of reaction, A plus B, and it goes to make products. We don't care. We'll say products because that just makes things easier. Okay. Now, the basic idea behind how we look at kinetics is to have A and B actually undergo this reaction. What happens? What do they need to do? So you have A floating around, you got B floating around.
They need to bond.
They're going to go do things, right? But what needs to happen before they can make a bond? If I have B out here and I have A here, can they do anything?
No.
What needs to happen?
They need to be together.
They need to collide, right? That's one of the big ideas behind concentration and kinetics, right? We need collisions, okay? If we increase the concentration of A and B, is that going to increase their frequency of collision?
Yeah, because they're all around each other.
Right, so to get a reaction, we need them to collide. If we increase concentration, that should increase the collisions, should increase the rate, okay? Now, was this necessarily a direct proportionality? If I took A and I doubled it, would it always necessarily double the rate of the reaction?
No.
No.
What was our little thing that told us about rate versus concentration? We had a special little equation that we had to figure out. So if we think back, what is this called? Rate is equal to K, concentration of A, raised to the X power. This had a special name. It's called the
Rate law.
rate law. Right, so this was our rate law. It had a lot of different parts to it, right? So rate was just the rate, the speed of the reaction, right? What was this little lowercase k?
It's a constant.
This was our little tiny rate constant, right? Not to be confused, constant, I was about to write concentration, not to be confused with the equilibrium constant. So the brackets, this was just saying concentration of A, concentration of B. What were these X and Y's? What were these exponents called? X here and Y here. What do we call this, these guys?
Aren't they like the?
These were the orders,
Yeah,
right?
first order, second.
Oh, jeez, that was wild.
So the orders were telling us the actual relationship between rate and concentration, okay? What can these values be? They weren't just
0, 1, and 2.
They could
0, 1, and 2, right? So these orders could be a 0, it could be a 1, it could be a 2. Why didn't we allow anything else? Why couldn't it be a 3? Term molecular reactions, how probable? So again, all this goes back to is these actual collisions. How probabilistic do you think it would be for 3 things to collide all at once in the proper orientation? You're really improbable, right? So these tend to just be 1, 2, or 0, okay? Okay, so if n was 0, we called this 0 order, right? First was 1, and then second was 2. Let's say that x here for A is 0. If I doubled A, what would happen to the rate of the reaction?
Wait, hold on.
Okay.
Okay.
If you doubled A, when we,
Wait.
So hold on, let me just write this down. So rate is equal to K A to the 0 power. What is anything raised to the 0 power?
0.
1.
1, right? So 1.
sorry.
So rate is equal to K, right? If I go in, and let's say I have a reaction, I double A,
It's still going to be 1.
what's going to happen to the rate?
It's still going to be.
It has what? No effect on the rate, right? So
Stays the same.
it stays the same, right? So we have a rate, let's say it's 1 molar per second. We go in, we double the concentration. This is still 1 molar per second. Doesn't change, right? So for 0 order, there's no effect of concentration. Is it E or A? I can't ever remember here. Effect. No effect.
E.
I probably shouldn't post that on my YouTube. I think, is it A?
I think
Yeah,
it's
it's
A.
E. No. E. There's no effect because cause and effect. That's the E.
Okay, continue.
Effect, right? It's a word. Who cares? Okay. So, rate. Okay. What happens if our little exponent was a 1, if it was first order reaction? If I double the concentration here, what overall effect am I going to have on the rate of the reaction?
Isn't it half the reaction?
Not half. If this is a 2
Uh-huh.
compared to a 1, this is raised to the 1 power, what's going to happen to the rate?
It's gonna be 2.
2, right?
So double.
First order, if I double the concentration, we're going to double the rate, right? So for a first order reaction, we are directly proportional. Direct proportionality. Now, what if the exponent is 2? What if it's second order?
That's 4 times.
Quadruple.
Right, so if I 2 times the concentration, 2 squared is 4, that will quadruple the rate, 4 times the rate. How do we determine those orders?
Oh.
How do we determine the rate law?
If you take like one experiment compared to another, and then you just go through that.
Oh, yeah, then
Yeah,
process.
right. So again, if we take an experiment, we compare it to another experiment, how do we have to go about determining rate law? Can we just look at a reaction and be like, oh, it's second order? No.
You have to like
Calculate.
This has to be determined experimentally.
And had its own little.
Yes.
Yeah, I took it. It was all over mine. I just took
So
it.
for the first, that's direct what?
Direct proportionality.
Direct proportionality. Okay, and the second one's Jen's concentrations 4 times the rate.
Yes. Quadruple 4 times, you know. It was easier to write 4 times as opposed to trying to think about how to spell quadruple, so. Yeah. I can't spell and write at the same time. Well, I can't really spell either, so. Okay, so that was kinetics, right? We had these rate laws, okay? This is going to be important, I guess, in terms of when we move into our first mechanisms, because a lot of the way that we know how reactions occur is because of rate. It's because of kinetics. Because, again, when we talk about mechanisms, this has to be determined experimentally, but this reaction doesn't have to occur in just one step, right? When we want to detail the sequence of steps for a reaction, we're going to propose a mechanism, right? And the overall experimentally determined rate law is always going to match up with the rate determining elementary step in our mechanism. And so again, this is going to be made a little bit more clear what I mean by this when we get to substitution reactions. Okay, so that's kinetics, and that's at least the effect that concentration has on rate. What else affects the rate of reaction? Concentration was 1.
Activation.
Right, so there's something called activation energy. There's also an effect with respect to temperature. That is not in our rate law, but where is it actually in our rate law? It's there, it's just not obvious. So activation energy, temperature, what component of our rate law does it actually affect?
Is the K?
The K, right? So rate constant is where temperature has an effect, and as well as the activation energy. Okay, so let's talk really briefly about those two things. Okay, so activation energy, where did that come from? So that was our little rate constant. So our rate constant, little tiny k, actually had a lot of different components. We're not going to talk about all of them, but I do just want to show you where the two things that we are going to talk about come from. Okay? So the first one is activation energy. And we abbreviate activation energy as E to the A. So E, A is this activation energy. If we go back to our little energy diagrams, we've already talked about reactants and products in terms of energy. This difference is how we represent enthalpy or delta G. What is the activation energy? Where does it come in at? It's something that we've ignored in the middle. Right, so the activation energy is the energy required to take our reactants and get them to this little point, this little top peak on the hill. What is that called? Transition state, right? There's another word for it. It's also called the activated complex. But the activation energy is the energy required to get us to the transition state or this activated complex. And I will abbreviate transition state a lot of the times. This little T with two crosses, tiny little T with two lines. What is a transition state?
That's an intermediate reaction.
It's not an intermediate.
No?
So transition states are usually hypothesized. They're these high energy complexes where the bonds that we need to break and the bonds that we need to form are actually all happening at the same time. So we're breaking bonds, we're forming bonds all at the same time. Again, transition states, because they're so high energy, usually cannot be isolated, right? You're never gonna see them as the highest energy complex in the overall reaction coordinate. Okay, so what is the rate of activation energy on transition or on rate of the reaction? The larger the activation energy, or the larger this hill is, the larger this energy required to get us to the transition state. What can you tell me about the overall rate of the reaction?
It's going to be slower.
Slower, right? So the larger this thing is, or the larger the activation energy, the slower the reaction rate. Okay. Now, other thing is temperature. Okay, so again, if we go back to this idea behind collisions and collision frequency, molecules to react need to collide, right? And when they collide, they're going to essentially have kinetic energy, because all molecules have kinetic energy. What does that kinetic energy have to deal with? Where do they get their kinetic energy from? So we're in a room of air right now. The molecules around us are moving. That's energy. Where's it coming from? Heat, like thermal energy, right? So these guys have this kinetic energy, they're colliding, right? If we have a really low activation energy, most of them on these little basic collisions can overcome that. That's where they're getting over this activated complex, right? If that activation energy is really large though, these guys are colliding just at normal temperature, they don't have enough energy to overcome that activated complex or that overcome that transition state. If we increase the temperature though, what happens to the kinetic energy?
There's more bounces.
Right, the more bounces, they have more kinetic energy, so now they're hitting each other harder, so now they have enough energy to get over the transition state to move actually to products, okay? So as we increase the temperature, we're also gonna increase the rate of reaction because we're increasing the kinetic energy of the molecules. We're giving more molecules enough energy to get over the transition state. So temperature, activation energy, are both very important in terms of rates. How can we increase the rate of reaction?
Increase the energy.
Temperature. There's a limit to that though.
Yeah, because
I think you guys did that last semester when you burnt everything in the lab. So there's a limit to increasing the temperature.
Yeah, because
Yeah, there's a lot of things we burn.
proteins up to
It was
nature.
on purpose, I would just like to say that.
Limit to temperature, limit to concentration, right? What is another nice little easy way that we can increase?
Add more reactants.
Catalyst.
Oh, yeah, more.
We can increase concentration, but again, there's a limit to that. So at the end of the day, we can also introduce a catalyst. How do catalysts work? They do increase reaction rates.
They lower the EA.
Right. So they usually offer an alternate pathway that lowers the activation energy, right? So now molecules at normal room temperature, instead of having to overcome this, can overcome these tiny little bumps, these tiny little activation energies. Yes.
That's with the catalyst?
That's with the catalyst.
Okay.
Is it so like how this helps push it and basically like?
Not push it.
Oh,
It alters
speeds
it in
up?
alternate mechanism.
Oh, so it lowers activation.
It lowers the activation energy by giving it a different pathway by which this reaction can go through that has these lower activation.
Does that make it faster then? with
Yes.
the catalyst?
Yes. Lower activation energy, faster reaction. And that's what a catalyst does.
What about buffers?
Buffers are just they're not gonna change the pH for you.
Wait, what's the difference
Oh,
between?
okay. I thought buffers would be similar with the catalyst, but okay.
Are
Just
these
keeps the
enzymes-
pH from changing.
Catalyst and enzymes. Catalysts are.
Enzymes are catalysts, yes.
Okay.
Enzymes are-
So I wanted to make one note here with respect to catalysts, is the fact that enzymes are biology's catalysts, right? They're proteins.
Okay.
Again, going back to biochemistry, or this idea behind biology and chemistry, all of our reactions that occur in biology are thermodynamically favorable. So life is spontaneous, right? But without the presence of enzymes, with the presence of catalysts, all of those reactions would be so incredibly slow that it would not exist. So one of the big early adaptations, or big early evolutionary steps, was the development of enzymes speeding up these reactions that were already spontaneous, but were just incredibly slow. Okay, yeah. So that's all I'm going to say today. So just, gnaw on that for a while.